We are now going to see another unsupervised method used to generate data based on neural networks, the generative adversarial networks. The paper at the top is a fundamental paper in which the authors design GANs. Let us present the generic framework of GANs. Assume that we have data, x1 until xn are ID, drawn from the unknown distribution P star. Our aim is to generate new data whose distribution is approximately P star, that is data that resembles the dataset at our disposal. GAN are composed of two devices that work together and against each other, the generator and the discriminator. The generator G takes low-dimensional noise, also called latent variables, as inputs, usually Gaussian or uniformly distributed, and turn them into fake data that closely resemble the original dataset. On the contrary, the discriminator D takes as input the original data and the fake data and tries to distinguish between them. The goal of the generator is to fool the discriminator, whereas the goal of the discriminator is to discriminate the true samples, x1 until xn, from the fake ones, the ones produced by the generator. This is an adversarial training. The two devices work against each other. One often used analogy is that of cops and forgers. You can see the generator as a forger who tries to create fake elements and the discriminator as a cop who is in charge of identifying the fake elements from the true ones. There is a competition between the forger and the cops. If the cops improve their ability to discriminate between true and fake samples, then the forgers are going also to develop their ability to create new fake examples. This game stops when an equilibrium is reached. The ideal situation for GAN is the one in which the generator has learned to replicate the original sample and the discriminator cannot differentiate true and fake data. One could then directly use the generator in order to create new samples. This picture has been taken from the original paper described before. You can see the generator and the discriminator. The discriminator takes as inputs real samples and fake samples produced by the generator, and the discriminator classifies each element as fake or original. Then the parameters of the generator and discriminator are tuned during the training phase to improve their ability to either generate fake data or discriminating between the fake and real data. The generator takes latent variables as inputs plus some noise, and it produces directly fake samples. GAN can be used for classical problems with tabulary data, but they are more commonly used to generate images. This is, in fact, the most impressive application of GANs. Let us now define the mathematical framework. In GANs, the generator and the discriminator are neural networks, parameterized respectively by theta g and theta d. The latent variables are denoted by z. For a given realization z, the generator outputs g of z theta g. For a true or fake sample x, the discriminator outputs a value d of x and theta d belonging to the interval 0, 1, which is the estimated probability that the sample x belongs to the original dataset. Now, the important question is how to train these networks, that is, how to estimate the parameters theta g and theta d. To solve this problem, we can use a log likelihood to evaluate the performance of the discriminator. The expectation of the log likelihood of the discriminator is given by equation 107. Indeed, the likelihood can be decomposed into two terms depending on whether the data seen by the discriminator is true, this is the first term, or fake, this is the second term. If the data comes from the true sample, the log likelihood of the discriminator is the logarithm of the probability that the data is labeled as being an original data, that is, the logarithm of d of x theta g. This should be integrated over the true distribution P star of the original data. In the second case, if the data is fake, then the log likelihood of the discriminator is equal to the logarithm of the probability that the data is labeled as fake which is given by the corresponding expression in 107. This quantity should be integrated over P of z, which is the density of the latent variables. We can maximize the quantity in 107 to find the best parameters for the discriminator. However, finding the best parameters for the generator requires to minimize 108, which states that the generator must fool the discriminator. Indeed, the generator is good if the probability that a fake sample is classified as a true sample is large. This corresponds to the term in 108, which is exactly the second term in 107. To summarize, we want to find theta g star and theta d star that are solutions of the optimization problem in equation 109, where the function to optimize is given by the expression below. So we have a joint optimization problem. Now, two small questions. For a fixed generator, can you prove that the optimal discriminator d star satisfies the first point? Besides, letting Cg being the maximum of Vgd over d, can you prove that the global minimum of C is achieved if and only if the distribution of the generator Pg is equal to P star, the distribution of the data? The answer can be found in the next sequence.